All right. Okay, so hi, welcome to this podcast. Today we have a very cool guest, and we have a PhD student, Andrés Arámburo. Andrés Arámburo is a PhD student at the University of Leiden. He works a lot of in computer simulation of cosmological problems, but more particularly, he focuses a lot in the problem of dark matter, which is what most of this episode is going to be about. On a more personal note, Andrés is one of my best friends, so it's actually really cool to have the opportunity to talk with him more in detail about his work, because I have a very general idea about what he does, but I don't know the exact details, so it will be very cool to know in a more detailed way what he do. So, hi, welcome.
Hi, I'm good. Thanks for having me. Yeah.
Yes, just a bit of a disclaimer. There's something a bit cringy about speaking in English with a fellow Mexican.
Yeah.
It was my idea. Anders accepted. I asked him and he very kindly accepted, but it's just to make it more inclusive, because I think in science,
Yeah, I mean, for consistent reasons, I think it makes sense. So yes, it's a bit awkward since we know each other since high school, and so we'll try our best to communicate as natural as possible in English.
All right, that's a good start. Okay.
Yeah.
Like I said, a lot of your work has to do with dark matter. So maybe in a very general way, if you could explain what is dark matter, what is the problem, what is this about?
Yeah. Well, before saying what is dark matter, which actually no one knows. I mean, it's one of the open problems right now in physics, in science in general, I believe. Maybe it's more important to ask the question why we need dark matter, or how did this concept of dark matter begin. In science in general, what we do is to, as many of your people know that listen to this podcast, we observe nature and we try to make a model that describes nature, right? And we usually start with the simplest model possible, and then we check with nature, and if it doesn't work, we have a problem. So in that sense, dark matter started as a problem, and it's still a problem. I mean, we thought that we understood, we think that we understood how the general law of gravity works, but while observing galaxies the rotation of galaxies, there was a discrepancy on the velocity. They were spinning faster than what their visible mass indicates. So, of course, in astronomy, we based most of our, now has advanced, but we based a lot of our measurements with light. So we can make an estimation of this galaxy has some brightness on different wavelengths, and with that we can estimate the mass. And that we can, with our normal laws of gravitation, we can guess what's the velocity that we expect, and we didn't have that. We didn't have what we expect based on the mass that we could detect in several orders of magnitude. So it turns out if you think about that this galaxy has some extra mass, that it doesn't emit light, so therefore it's a dark matter, it solves the issue. So this is how it started, but with later more evidence on or more observations with the universe, this dark matter started to fit some other problems that we were observing on the universe. So there's further evidence than the rotation of galaxies. There's specific objects such the bullet cluster, which is which broadly speaking, uses another technique that is also something that it's a good thing for dark matter, which is called gravitational lensing. So this is from general relativity, we know that light travels in geodesics, and that mass curves space. So sometimes when we observe, we see that there's some distortions of light, and there's no a clear source of this mass, so we assume it's dark matter. So this is one of the few things. There's more sophisticated proofs or things that we need dark matter. Well, proof is a strong word. Things that we need that dark matter solves, such as measurements on the cosmic microwave background and the structure formation of the universe, but maybe I will touch that later.
Okay, so yes, maybe in a general way, like yes, that there's a series of observations, astrophysical observations that don't really fit the theories of the, I don't know, gravity or general relativity, at least unless you include this extra matter, right? That would be like a general way.
Yes, I guess that a way of seeing it is we have a problem,
Yes.
and we don't understand, right? So we proposed that there's a mechanism that solves this problem. Then I guess that you have like a two choice. One is to introduce that this dark matter, because you have to ask, well, what is this, right? So you have, let's say there's two schools, or there's more, but let's keep it simplistic. One is this dark matter is made of a particle that is unknown for us, that we don't know what it is. Or our understanding of the law of gravity is wrong, which is the modified gravity approach. So I guess that you have to choose like your Occam razor, like what's the simplest thing to introduce a particle, or if you think that it's simpler to explain all this with a series of modification of our understanding of gravity, and different people have made their decision on what to fight for in this mystery.
Okay, so you mentioned Occam razor, like basically choosing like the simple possible explanation, how to say it. And I guess in this case, the fact that general relativity has been incredibly successful, that's what that would be one of the reasons that you decide, rather than modify gravity or see that there is a problem with our current theories of gravity. That's one of the reasons that you would love for adding this dark matter, so to say it.
Well, more than that, I think that historically speaking, dark matter as a particle is a bit of a more comfortable way of approaching the problem. And I can try to share like my thought process. Also, there's a bit of a disclaimer here, like a bias disclaimer. In all my cosmology courses, and my supervisor believes in dark matter as a particle. So I have been heavily conditioned to believe that, or more than anything, I've been more exposed to the size of dark matter as a particle. So if it's a particle, then what do? You go to particle physicists, right? These people are the people that know about what matter is made of. So we check on the standard model of particle physics, which is a super successful model of describing a lot of things. I have made a lot of predictions, the Higgs boson, etc. And ask them, okay, do you have a particle that you know that it exists that can fit on dark matter? And for some time, dark matter doesn't, you want it to be charge neutral, massive, difficult to find. So some people thought, oh, neutrinos are perfect for this, it's all that. But it adds up with current evidence that neutrinos cannot do it. There's several reasons why not to. It's related with structure formation, properties of neutrinos, things like that. So neutrinos were not. So if we need a candidate for a dark matter particle, we need to go beyond the standard model. And that's how it's called, like this field, an extension of the standard model, or beyond the standard model things. So, but there's extra encouraging things, because the standard model of particle physics, even when it's very successful to predict a lot of things, it has some problems. Mainly, in the standard model of particle physics, neutrinos have mass equal to 0. Okay. And if you add mass, it's problematic. But we know by measurements that neutrino has mass.
Okay.
An additional problem is that we live in a universe that is mostly populated by normal matter and not antimatter. And this is called the matter-antimatter problem. And in the standard model of particle physics, the laws of physics apply exactly the same for both sides. So there's no mechanism or no reason why there should be like this discrepancy in the abundance of antimatter and matter. Okay. So having these problems, and actually for other sides saying like, oh, we need a particle that is not described by the standard model, is kind of, I guess that for a lot of people was like, 1 + 1 = 2. We extend the standard model. We will find this particle, and we, in the process, also fix the current problems that the standard model of particle physics has.
Okay, see, and I mean, it clearly it's a complex problem, and you mentioned a lot of the research is about to find first of all, if it's a particle, then what kind of particle it is. And actually, I'm an expert, but I mean, I think like a lot of experiments have been done, or like very like underground laboratory, super complex thing to search. I don't know if that's related to neutrinos, but to search like a sort of like, yes, experimental evidence of particles related to dark matter, but it has been proven like extremely hard. So far, I think it has not been successful. So it seems like it's very complex if it's a particle, it seems very difficult. It seems very elusive, I would say, very difficult to detect in any kind of way, I would say.
Yes, exactly. So there's like several points of your answer. I think that about the underground thing, you're talking about neutrinos. And part of the neutrinos has to do other interesting aspects of cosmology, the relic neutrinos and things like that. And also to measure if they really have mass, right? Because if it's a big problem, so you really want to verify that it has been verified, okay? And one other of maybe a biased of why 20 years ago or 30 years ago it was very promising, the idea of dark matter as a particle, is that, well, we had all these plans of LHC and huge accelerators, and LHC was successful because it found the Higgs boson, but also a lot of people that had all these particles, not only dark matter, for other problems on physics, they didn't appear, right? So it's a problematic, and I mean, there's efforts in the LHC to design detectors that could find a particle that meets certain criterion.
And I guess it will be hard to say, but honestly, until now, yes, obviously LHC it is very important, and it was able to experimentally prove the existence of this Higgs boson. But I don't know, like for me, it seems a bit unlikely that a new particle will appear soon at the LHC at the energies they measure. So I don't know if it will be too speculative to say that it seems unlikely or unlikely.
I mean,
particle years.
To be honest, I'm not a big expert on that regard, so I'm not able to provide how likely or not is to that. There's like this notion, simplistic notion maybe on particle physicists, in which that if they don't have their particle, they say that we just need more energy and push energy. But I think that to find this dark matter particle, you can have two complementary approaches. You can have like accelerator physics, and the other you can have a huge accelerator, which is space, right? So that's more or less where I move around, right? And about possible candidates of dark matter particles, there's been some, I mean, particle physicists have done their homework, let's say, in proposing particles that they can fit in these problems of the standard model of particles, and also fit in some cosmological situations that we need. So there's something called the cosmological standard model, or the standard model of cosmology, which is referred as lambda CDM, which lambda means it's the cosmological thing that refers to dark energy, and CDM is called dark matter. So it's currently, let's say, the model that explains a lot of things, but also is the most simple model. So that's also a very, in physics in general, we like simple models, right? Because they are simple to work, and they have the less free parameters you have, it's easier to understand things. But so something interesting about this, maybe that catch the attention, is the aspect of cold dark matter. Like what does this mean, really? So for that, I think that way to explain it is through structure formation, meaning the process in which in the universe we have structure, we have galaxy cluster, galaxies, etc. So how does this happen, or how is the current idea of how it happens, because absolute terms is not a nice thing in science. So the current thing is that the universe at the beginning was not completely homogeneous. Okay. There was small density overdensities, perturbations that let's not think about dark matter or anything. It's just you have small densities, they grow. Matter, let's say normal matter, falls into this perturbation, and it starts getting clustered, and then suddenly you have structure. You have clumps of that. But the problem with that is that in order for have normal matter to collapse, that's how it's called. We call it.
I think.
Clump. Just to clump to form structure, you need the matter to cool down, because if it's very warm, you have pressure that is fighting gravity, and it needs, in simple terms, let's say it needs times to cool.
Okay.
So in our current understanding on the evolution of the universe, we know that structure formation happened in a time in which, without any additional help, let's say, we will happen earlier than expected, like without any help. Like if we don't add this, we will expect that the galaxy formation and all this happen later than what we observe. Okay. So then is another situation in which dark matter it helps, because since dark matter do not interact, or if it interacts is very loosely with radiation, then it doesn't have this problem, right? It can fall into these overdensities and help these overdensities, clunk these halos, and then gas will fall into them, right? So it's like an extra help with that. And now, what's this thing about cold dark matter, warm dark matter, hot dark matter? So this maybe, even when we make an analogy like with temperature, maybe it can be thought as temperature as like in the sense of kinetic energy, let's say, not in radiation of black body, blah, blah, blah. So it's, so cold dark matter means that when it started, it was not relativistic. So the velocity was not relativistic. Okay. And the warmer it gets, the more relativistic state. So, if why is matter that if relativistic or not is that because if you are traveling in relativistic speeds, you cannot fall into these densities. Okay. So the cooler it gets, the smaller these perturbations they can fall in. Okay. So
no, just I just want to clear up, because I think a lot of the attention gets into the gravitational effects, and obviously they're super important, but it seems like it's not only about the gravitational effects. Obviously it's very important, but it's also, I mean, a lot of the research to see the properties that dark matter can have. You talk about cold dark matter, warm dark matter, so there's all kind of properties besides the purely gravitational effect.
Yeah, this thing. Yeah, exactly. So just to finish the idea, yes. Based on how warm or cold it is, you can establish a length that is called the free streaming length. That is the average distance that a dark matter particle can travel before falling into one of these speeds of these overdensities. Okay. So the smaller this length, the more of these small clumps you can have. But if you have warm dark matter, then you don't have as many of these small clumps. They fall into bigger clumps, let's say, because the other got washed out. That's how they call it. So in this way, measuring, let's say, how many of these small or big clumps we have, it's a way of establishing or trying just to understand the nature of dark matter. Okay. And sorry, if it's yes, as you said, if it's warm or cold, this helps to establish the possible candidates of the hypothetical particles that people have proposed. So, so for example, for warm dark matter, people have proposed something called sterile neutrinos. For cold dark matter, there's axions, and I mean, since they are hypothetical particles, there's a challenge of defining parameters from these things, but the mechanisms that they are described with and how they fit with the beyond of standard model thing helps to establish if they are warm or dark or which special properties they can have.
I see. And I don't know, for example, between these two options of warm dark matter and cold dark matter, are there some scenarios when, I mean, you clearly mentioned the clumping, so I guess in most scenarios, maybe the cold dark matter will be more a better approach, but is there some scenarios where warm dark matter could be better, better candidate? So
well, actually, that's one of the current approach to constrain dark matter, in the sense that exactly with that logic is, okay, if we have cold dark matter, then we expect that we have more smaller structures in the universe, the smaller dark matter halos. And if we have warmer, then these structures are not there. So we expect that if we make something called the matter power spectrum, which basically just tells you how much of certain size structure you have, we will observe like a cutoff in smaller structures. In cold dark matter, like let's say in a simplistic way, it allows you to have arbitrary small structures, but in warm dark matter, depending how big is this free streaming length, you have a cutoff in smaller structures.
Okay.
So actually, that's a current tension on the nature of cold dark matter, because it's referred as the satellite problem, or in general that when we make observations, we don't see as many of small clumps as computer simulations of dark matter only will suggest. But there's also the argument of, well, these very small things are very complicated to observe. So maybe it's just that we currently don't have good tools or good observation skills to measure these things.
Okay, so yes, I mean, obviously in science, historically, there's always has been this feedback between experiment and theory, in the sense that sometimes with new theory, you can create new experiments, and sometimes with these new experiments, give you new information, which can develop new theories. So I guess, I'm guessing there are a lot of projects, or not at least a few, so I don't know. I guess the question is, how optimistic are you about the new projects or new technology that could help the theories to give more evidence, more observations maybe? I don't know.
Yeah, so actually I think it's a quite exciting time to be around thinking about dark matter, because one, you have the James Webb Telescope that was just launched, and more importantly, soon there's ESA space instrument called Euclid that hopefully will be launched soon, and hopefully it will survive, that especially what they are going to do is to do a lot of weak gravitational lensing. So since these small clumps are hard to observe, let's say by light, the idea is that gravitational lensing, that it only measures mass in a very smart way, we'll be able to have a chart of more of these small clumps if they exist. And if they exist, then it's a strong points for cold dark matter, just we didn't see it. If we don't observe them there, then we need an alternative thing. Maybe it can be points for warm dark matter. Just I don't want to forget about, there is also hot dark matter, which is super relativistic, and just based on our understanding on the evolution of the universe, this is not feasible.
Okay. Is there a particular reason?
Well, the thing is that this wash a lot of structure, and first it favors very large structures and not smaller. So it's just not what we observe when we see the sky.
Okay, I see. And for example, you talk about observations that could help in, maybe have a bit more evidence or help with theories of dark matter. Could there be any evidence that discards dark matter? Or is there any type of evidence that could say, okay, maybe this is not, I don't know?
Well, that's complicated, right? Because, I mean, I guess it gets back to the original question, right? I mean, I think that there's no like one single piece of evidence that will say that all these problems that we need dark matter are fake. Okay. Let's say it's a real problem, we have to explain it. If dark matter as a particle, let's say, to get completely discarded, then, well, the way is to propose a simpler model that corrects all these things, right? And or maybe we need a combined approach, right? Who knows? It's up to active research to do that. But one of the things is that dark matter as a particle really solves a lot of early universe situations and very strong evidence we have. Like one of the best measurements we have, that is the cosmic microwave background. And a lot of it's amazing the amount of cosmology and things about the universe that you can learn by the analysis of that. It's, I think, in my opinion, one of the biggest achievements as monkeys that we have made. But that there's if you analyze the temperature, you can do special analysis of the power spectrum of the temperature, and then you can, based on that, you can establish ratios of the contents of the universe. Okay. So one of the ratio is 30-something lambda matter that it constitutes the matter, dark matter and baryonic matter, which is we call the normal one. Okay. And we just don't have enough baryonic matter to explain for the rest of the thing that it needs. So this is very tightly constrained. So I think it will be quite complicated to, at least on my understanding, which also, I mean, I'm a PhD student, I'm not a renowned expert on the topic, and being an expert on this topic is completely very, very difficult because there's a lot of things to have in mind. Mm-hmm. On my thing is that there's no modified gravity that can explain these CMB peaks. Okay. So that doesn't mean that gravitational laws are perfect. Mm-hmm. Maybe it can help in certain ways, but at least it's a very difficult challenge.
Okay, I see. And I mean, it's not my area, like just a bit of a naive question, but like, I don't know, at least my impression, a bit naive impression, but I feel like maybe the field could benefit from maybe a closer collaboration between researchers of the area of modified gravity and maybe more proponents of dark matter. Do you consider that there is a close collaboration or not that much, or is it like more like each group goes in its own direction? I don't know. What's your impression?
Well, I don't know. I mean, I know, at least in my institute, that soon two people that work in like the different fields will share a PhD student to work in something like that. Mm-hmm. So, I mean, close evidence that the attempts have made, but a lot, I mean, as scientific as we want to sound, scientists are humans. Humans have their biases. They like to have their things. Sometimes making two people that disagree on that is, I mean, in any topic of life, politics, ethics, religion, or whatever, is complicated. And also in scientific, even when we want to think like, yes, I'm a man of evidence and all that, sometimes making people talk is complicated, right? And also, but yes, I mean, it's not like, I don't want to make it sound like the modified gravity people are like crazy people or whatever. There's very, very smart people that are supporting modified gravity, and discarding their knowledge and their intuition, it's just irresponsible. But yeah.
Okay, I see. Well, if it's okay for you, I don't know if you would like to talk us, because now you have explained a bit the general idea of dark matter, some of the problems about the positive aspects or evidence in favor of dark matter. But maybe if you could tell us in a more specific way, because I know you do computer simulations, but maybe a bit in a more specific way, what is it that you do exactly in your research?
Okay, so I think earlier you were saying something about matching theorists and observational people. And I think that in cosmology, at least, there's a sweet middle ground called cosmological simulations that kind of fits in both ways.
Okay.
So the idea is that we only have one universe, right? So it's in cosmology, we have one experiment that is running, right? So it's not like we can go to the lab and create a universe. So the way that we have try to play with this, in a sense, is that to try to make simulations of the whole universe, which are called cosmological simulations, in which, of course, simulating the universe is a titanic task. It's very complicated, and of course there's compromises. We cannot simulate each atom of the universe, and different simulations have different purposes, right? There's dark matter only simulations that don't include gas, but currently we have very good hydrodynamic simulations that has components of dark matter, that have components of gas, stars, as mechanisms of star formation, and that they reproduce observational data. Okay. So, for example, we create good statistics that match the amount of galaxies that we observe and things like that. So, cosmological simulations, let's say in a very simplistic way, is solving the universe from a very early age, with perturbations and then growing structure and up to the current time. Okay. So these are things that are run in supercomputers that require a lot of manpower to create all these sophisticated models that recreate a lot of physics that are done in that are needed to simulate an accurate representation of the universe. And well, you need computer scientists, software engineers that are very smart with code, because you need to be as efficient as possible. So yes, so in that way, I think that cosmological simulations have helped in the sense that it gets fit from the observational realm, because it allows us to know how accurate our simulation is and how much you can trust it to utilize results, because you generate insane amount of data of different snapshots, that's how we call it, of moments in time of the universe. So you can say, okay, I'm going to do analysis of the universe at redshift 3 or something like that, okay. Right? So, but of course you need to know how realistic are they, but also you need theorists to work on them. And also it's a way of trying to constrain some theorists from some theories from theorists. Okay. So in what I do, which to answer your question, in my group, there's people that are very theoretical, and they are very acquainted with these dark matter particles, right? And so we have used computer simulations to try to constrain a bit the particles that they could exist. Yeah. So,
Okay, so you talk a lot about you do simulations, but for example, I'm guessing you look at the dynamics of certain system, or is it like evolution in time of certain system? Or
no, it's a cosmological simulation. So you have a lot of galaxies that interacting. You have a cosmic web, the famous image that there's that people say is neurons and things like that. You have that, and you can zoom in to a galaxy.
Okay.
Right? But there's a lot of parameters, right? There's there's some mean simulations in which first they resolve broadly some aspects, and then in interesting objects they rerun it with higher resolution, so you have more realistic things. But talking about realism is complicated because it depends on what you are interested in, right? So yes.
So yeah, I mean it's simulation. In the simulation, you try to obtain like sort of like a visual clues, so to say, about the distribution of galaxies, for example.
Yeah. Okay. I can put a precise example of a work that we made. So this is going to sound esoteric, but okay. But that this is how it works, right? So one mechanism that okay. So there's like this might be this idea that dark matter is not completely dark, let's say, but interacts with photons in a very rare occasion.
Okay.
So there's this particle that is being proposed that's called a dark photon.
Okay.
Okay, and so the idea is that in very specific occasions, this dark photon can interact to a photon.
Okay.
So a photon goes to a dark photon or the other way around. Right. So when is this maximized? So okay. So this person has like worked the theory and said, okay, this probability, even when it's small, is maximum when the mass of this dark photon is equal to the effective mass of a photon. Okay. So first, what are we talking about? Photons don't have mass. So what this means basically is that a photon in a charged medium, it gets dragged. So it's effectively has like a mass, right? So photons in a charged medium can have an effective mass, and if it's equal to this dark photon mass, then this conversion can happen. Okay. So what we did is that we grab a cosmological volume that evolves in different parts of redshift, and then we generate sightlines. So we started looking at different parts of the box.
Okay.
So in the simulation, we have we can calculate the electron number density. So in these areas, we will expect to have a higher probability of this conversion to happen. So in this way, of course, we don't know the mass of the dark photon, right? So we can play around with that and say about these mass ranges, if we detect some light, we should expect some missing photons, or because they converted into dark photons. So in this way, you can play the game of we haven't detected, so you constrain further the mass of this particle. So you create constraints that help you rule out or help you to explore in more particular things. So that's a work that we already put out, but currently we are working on let's say a bit more ambitious version of it, in which we have a very, very long simulation.
Okay.
And the idea is, I mean, it's 1 gigaparsec, something like that. And it's the same idea, but we want to match it to the instrumental resolution of the Planck satellite or the South Pole telescope, which were the ones that measure the CMB.
Okay.
So the CMB it's very well defined, so it has, but of course it's an instrumental error, you have some leeway. So the idea is that to match this resolution to see, okay, the CMB emits photons. If these photons turn it into dark photons, we expect that expect some deviation from what we observe. So this has to be within the measured constraint. So in that way, you can constrain even further the mass of these things. But you can also do and we have done a similar analysis with axions, which is a cold dark matter candidate. But for that, you need magnetic fields. It's like a similar logic, but also with magnetic fields. But for that, you need a simulation that creates magnetic fields.
Okay.
Right? And during that process, we saw some behavior on these magnetic fields on the large-scale structure that, well, it's within your simulation, but is observing magnetic fields on the cosmic web is still an ongoing thing. So let's say that's a case scenario in which we can be able of, once we would say to the observation or simulation, produce this. And maybe they will say, okay, whenever they can measure it, no, something is off, it's bigger than you expect, blah, 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 blah. So this is a scenario in which you fit the field in both ways, right?
Okay, and I mean, you mentioned these dark photons. Is this a proposal only from the dark matter community, in the sense like, is from the side of particle physics? Is there also studies from this perspective, or theorized from this perspective, or is only more from uniquely from the field of dark matter? Because if it's a particle, I mean, it's gonna
No, of course. I mean, I think that these people, when they propose these things, they also want to address some problems on the standard model of particle physics. Okay. So I think that they always take it in mind to solve some issues. But yeah, I mean, it's complicated, right? Because as I said, for example, this mass parameter, you can vary this thing, right? So it's a very free. It has a lot of free parameters, but our job is to try to constrain them in order to be able to rule it out or get the lottery and find it, right? But yeah.
Okay, I see. And I mean, obviously, it's very difficult, and it's a difficult problem, obviously. But I don't know how it's hard to say like a precise number, but like, how optimistic are you of actually discovering or knowing what is dark matter in the near future? I don't know. I know it can be very speculative, but I don't know.
I mean, to be honest, I think it's very difficult to assess that, right? I mean, yeah. I mean, I think that we in the near future will make some progress on constraining the nature of it. As I mentioned, with the Euclid, will help us to see how much of a problem is this missing small halos thing. Okay. And it can be a super good points for cold dark matter or not, or heavily constrained warm dark matter, which will be helpful in both ways. But I think no one can predict like when it's going to happen and how. Maybe I'm missing it tomorrow. Someone publish something, right? So in that way, I think it's very exciting. It's an exciting field in the sense that the amount of things that we don't know is a lot. So that means that physicists and astronomers and cosmologists and people that make instruments have a lot of work to do. And yeah, I mean, it's not like something that is we are just retesting things that we know, right? It's something that we have to explore, that we have to think about, and need smart people to work on.
Okay, I see. And I know that your approach comes more from the dark matter side, but still, just maybe in a very general way, if you can talk about maybe, because I mean, the other option is basically modified gravity. Do you know any of the most convincing proposal or the main candidates, or is this not? I know it's not directly your area, so it's difficult to answer, but I don't know if you have heard about some particular approach that seems more promising, or?
No, to be honest, it's. I mean, I'm part of the problem that I'm not very acquainted with the conversation that is happening in modified gravity. I should have it more, but yeah, I think that there's no model that explains a lot of the problems in one single way, but I might be wrong that there's very. And also, I think that since I'm involved in the cosmological simulation side, I will say that, at least on my impression in the field here in Europe, mostly is focusing on treating dark matter as a particle. There's people that make simulations with warm dark matter in different models and see how the universe changed with that. But also, I think it's helpful maybe in the simulation side that assuming this is the easiest way to reproduce a universe that looks like the one that we have.
Okay, I see.
And computationally is, I mean, having a particle that only deals gravitationally is good, because it's not very I mean, it's expensive, but it's not the most expensive thing in the simulation compared to trying to calculate thermodynamical stuff happening.
Okay, I see. Well, I mean, yes, I mean, I was gonna ask you about the future of the dark matter research, but you mentioned it. Like, I mean, yes, it's a difficult problem, but I mean, researchers are trying to find out this question. There are new experiments that you mentioned. So yes, while you cannot really know with 100% certainty when or how will we know the right answer, so to say it. I mean, it seems like at least the field is advancing, and there has been progress. And yes, I mean, at least we're trying to find more constraints. Well, you're trying, and the scientists are trying to find at least to find constraints and to see which properties, which could it not be at least.
Yeah. I mean, it's a big problem. Maybe sometimes we ask too much as a bunch of monkeys in an important part of space to understand so much about the universe, because I mean, it's amazing how much we can learn just talking to each other and using computers and things like that. But yeah, I mean, I guess that right now I'm just a part of a group making a very small contribution to try to solve this big problem that we have currently in physics and cosmology and our understanding of the evolution and of the universe.
But it's very cool. Okay.
Yeah.
Okay, so yeah, very cool. I don't know, maybe on a last note is, yes, because you're a PhD student, maybe, I know you don't like to give advice, but I feel like you have, from the time that I've been here, I feel like you have found a really good balance between research and actually having a social life and live. So I guess you don't like to give advice, but I think you will be good.
Yeah, maybe you should not say that. We should not publish this, that I have a social life. No, I study all that. I devote my life to archive. Yeah, I mean, it's complicated. I won't say that it's not complicated. I guess that at the end, it's a personal decision how much you want to contribute to the field. Let's say, I mean, there's very devout people to the field. Maybe I'm not the most devout person, but I guess it's just a matter of assessing your priorities, right? If you are happy with doing a small progress on the field, but still pushing, you can do that. Or if you are happy with being a monk of dark matter and devoted to it, it's also possible, right? But it's just a way of adjusting your expectations, I think. But I'll say it's possible to have a balance in both things, and I think that more and more people are searching for that balance.
Okay, I see. And I mean, obviously, I like to explain the cool aspects of science, how amazing it can be. But I mean, because you mentioned about finding this balance, and also I guess the truth is that the field can be very competitive sometimes. So, for example, if you're trying to search a postdoc, normally the number of positions is much less than the number of applicants. So it's in a way, the truth is that in a way it's a competition. So I mean, in a way, it's very great that one can find this balance, but at the same time it can be hard in the sense whether you like it. That's a competition.
That's totally true, and that's, let's say, the sad truth. I mean, there's a big problem in science right now. I mean, a lot of extremely devoted people that are extremely good, they have decided to change their career because maybe the academic work was asking too much of a personal toll to them to move to a different country again. They have partners that sometimes it's complicated to tell them, okay, I have a job now in this part of the United States, we are moving. So I think that academia has to be a bit self-critical to address these problems, but also it's not complicated to I mean, of course, I think most of the scientists will say, let's get all the postdocs we want, let's get a lot of things. But I mean, a lot of this is politics to get money to be able to host these people. But I mean, it's a complicated issue. Yeah, I mean, and in a way, sometimes I guess it can feel that science exists. Well, I mean, no one studied physics to become rich, or at least at certain level, right? It's because people are very passionate about this very human task of understanding. But it seems that really academia is really driven by very passionate people, because otherwise, if they were not passionate, they will be earning a lot of money because I mean, these people are very smart, and they are very useful for solving problems, and the world has a lot of problems to solve. Some of them give you more money than others. But yeah, and also I'll being like the advocate of the devil, or the counter advocate of science. I would like, if my advice is worth for anything, that people that work in science, a lot of times I think that they are a bit worried about leaving academia because they have devoted a lot of time into it. You know, you do a bachelor, you do a master's, you do a PhD, a postdoc, you go to schools, you survive in some places with not a very good salary, etc. But that they are super smart people and capable of migrating, and their contribution probably will be very valuable in different aspects of life. I mean, I think there's this worry that if I don't do academia, then what? I say that you are smart and you can do it. I mean, it's people. Yeah, and science gives you a lot of skills, so that are appreciated in different fields. So
yeah, I guess you should not see like if you don't continue in academia after a PhD or maybe after a postdoc, it's not the end of the world. There are other things that you can do, and yeah, I mean,
and there's a lot of people that have experienced that, and that they are living happy lives, and also that doesn't mean that they don't like science as much as someone that stayed or all that.
Okay, really cool. So I think that's it. But honestly, it was very nice to know more precisely what you do. So thank you very much.
Yeah. Hopefully it's useful for anyone, and hopefully I didn't say a lot of lies.
I think I care really. Okay.